Good morning. When we try to solve complex logistical problems in computer science, we often look to nature for inspiration. Today, we're going to look at swarm intelligence, specifically focusing on what we call ant colony optimization. To understand the computer science, we first need to look at the biology. If you isolate a single ant, you will find that its physical strength is impressive, but its cognitive awareness is practically non-existent. An individual ant has no memory of where it has been and no concept of the wider environment. Furthermore, unlike a human corporation or an army, an ant colony has absolutely no central leadership. The queen does not give orders. She simply reproduces. So how does a colony of millions find the shortest, most efficient route to a food source? They do it chemically. As ants wander blindly, they leave behind a trail of chemical pheromones. When an ant randomly finds food, it walks back, leaving a stronger chemical trail. Other ants smell this and follow it. The shorter the path, the faster the ants travel back and forth, and the stronger the chemical scent becomes, quickly drawing the entire colony to the most efficient route. In the early 1990s, computer scientists realized this biological trick was a stroke of genius. They began writing software that mimicked this exact behavior, turning the physical scent trails into mathematical algorithms designed to solve complex routing problems. However, translating biology to code wasn't simple. If a computer finds a good route early on, it tends to stick with it, ignoring potentially better options. To fix this, programmers had to copy another quirk of ant behavior. They intentionally programmed a high level of randomness into the software. This forces a small percentage of the digital ants to constantly wander off the main path, ensuring the system is always exploring alternative options, just in case a better shortcut exists. The industrial applications of this are massive. In the late 90s, the first major adoption of this technology wasn't in transport, but in the digital space. It was used to route data packets through massive telecommunication networks. If a main server crashed, the ant software would instantly and organically find a new path for the data, preventing total internet blackouts. Today, physical transport companies rely on it. A major delivery corporation might have millions of packages to deliver across a single city. Using human logic to map out the perfect route for thousands of trucks is mathematically impossible. But by running an ant colony optimization program, these companies can calculate highly efficient daily routes that bypass traffic jams, resulting in a spectacular reduction in overall fuel consumption, saving millions of dollars and lowering emissions. We are also seeing this applied to aviation. As the skies become more crowded, human air traffic controllers are reaching their limits. Engineers are now utilizing ant-based logic to program collision avoidance systems for swarms of flying drones, allowing hundreds of them to navigate the same airspace smoothly, without human intervention. Of course, the system isn't perfect. Because the software relies on millions of digital ants blindly wandering around until they establish a strong connection, the very beginning of the computing process is frustratingly slow. If you need an instant, split-second calculation, traditional computer logic is still much faster. However, looking to the future, the potential is life-saving. Urban planners are exploring how to integrate this dynamic, self-organizing software into smart cities. Instead of relying on static, pre-programmed maps, the ultimate goal is to use this technology to coordinate ambulances and fire trucks, guaranteeing the fastest possible emergency responses regardless of unpredictable road closures or accidents.